This is part 3 of lecture 22. In this lecture, we are discussing Laplace transform of partially defined functions and step functions. So in the previous parts, we discussed how to write partially defined functions using unit step functions. So let's remember, recall unit step function. So for a positive constant c, a unit step function at time t equals c is the function which takes the value 0 if t is less than c, and the value 1 if t is greater than or equal to c. And if we have a function g of t, which is, let's say, a function h1, if t is less than, say, c1, a function h2, if t is between c1 and c2, a function h3, if t is between c2 and c3, and if it may be an infinite, remember, piecewise continuous functions on infinite intervals, as long as on any finite interval, we have only finitely many of those points ci's, it is possible to continue up to infinity. In this case, we can write the function g using the unit step functions. So we start with the function h1, and then we take the first discontinuity. It doesn't have to be discontinuous, of course, at the point c1. That's the only, okay, maybe I should say seam point or break point for the function g. So it is at c1. We take the unit step function at c1, and then in front of it, we take the function h2 minus h1. And then next one is unit step function at 2. We take h3 minus h2. And next one is c3. We take h4 minus h3. And so we have infinite sum like this. If it's finite, then we have a last term. We stop at the last point. But if it's infinite, we can keep going. Okay, so last time we did examples, but function with infinitely many discontinuities. Let's say the function g is what we call the square wave function. So it takes the value 1 if t is between an even integer and odd integer, and it takes the value 0 if t is between an odd integer and the next even integer. Okay, so it is like, as long as Laplace transform is concerned, we only care about positive values. So 0 is even, 0, 1, 2, 3, 4, and so on. So our function between the interval from 0 to 1, it takes the value 1. One moment. So let's say here is 1. So our function, it takes the value 1 from 0 up to 1. And at 1, the value drops to 0, and then the values are 0 up to 2. And at 2, the value jumps to 1, and stays 1 up to 3. And at 3, it jumps down to 0 and stays 0, and so on. So it keeps going like this. So using unit step functions, we can write g of t. G of t. We can write g as, we start with 1. The first function is 1, and then plus the first point is at u1, the first break, and the value from 1 to 2, the value is 0. So we take 0 minus, from 0 to 1, the value is 1. And the next one is u2. From 2 to 3, the value is 1, minus from 1 to 2, the value is 0. Plus u3, 0 minus 1, plus u4, 1 minus 0, and so on. So our function g, then 1 minus u1 plus u2 minus u3 plus u4, and so on. Okay, so it can be written as an infinite sum like this. For finitely many scene points or discontinuities, we did such examples in the previous part. Okay, so now the question is, what is the Laplace transform of the unit step function? And then we are going to generalize this. We are going to multiply a unit step function with another function to treat the above examples. Okay, so we are going to use the definition. It is the integral from 0 to infinity e to the minus st times the function. But the unit step function is 0 from up to c. So if we divide this integral into 2, if we take from 0 to c first, then the unit step function is going to be 0. And then from c to infinity, the unit step function is going to be 1. Okay, so the first integral is 0, of course, and the second integral, ni derivative of e to the minus st, with respect to t, we take minus 1 over s e to the minus st. Oh, I'm sorry, I need to do the limit thing. So the first integral is 0 plus limit as m goes to infinity of the integral from c to m e to the minus st dt. So limit as m goes to infinity, minus 1 over s e to the minus st for t from c to m. And then minus 1 over s e to the minus sm minus e to the minus sc. And as long as s is positive, the only limit, the only part with m is the term e to the minus sm, and this will go to 0 for positive s. So this limit is going to be e to the minus cs divided by s for positive s. So Laplace transform of the unit step function is e to the minus cs divided by s for s positive. Okay. Now, of course, to treat all the other partially defined functions, we need to figure out the Laplace transform of a unit step function multiplied by another function, say h of t. Okay. If we try to do this, okay, let's use the definition from 0 to infinity, e to the minus st, uct, ht, dt. So up to c, the step function is 0. So we take only from c to infinity. And from c to infinity, the unit step function is 1. So we have e to the minus st, ht, dt. Now we want to say that this integral is the Laplace transform of h, but not quite, because in order to be the Laplace transform, the lower limit of integration should be 0. So we can make a change of variables. We can let u to be t minus c. Then, first of all, du is equal to dt. If t is equal to c, then u is going to be 0. So with this change of variables, we change the lower limit of integration to 0. And as t goes to infinity, u also goes to infinity. So we can write this integral in u. So we were doing Laplace transform of uct times ht. So from 0 to infinity, but now instead of t, we write u plus c. So inside h, we have u plus c, du. Okay, so the exponential part, we can separate SU and SC. SC, the integration, the variable of integration is U. So we can, it's like a constant. We can take e to the minus SCS out of the integration, minus, and then e to the minus SU, h of u plus c, du. Again, not quite. So we call, all right, we call this h of u plus c, we call it f of u. So let f of u be h of u plus c, so that f of t, so what is u? Remember, u is t minus c, and u plus c is t. So if I let f of u to be h of u plus c, then h of t is f of t minus c. Now, Laplace transform of uct, ht, this is the e to the minus cs times the integral e to the minus su fu du. But now u is just the variable of the integration. So u is the variable of integration. So this is going to be, wait a minute. E to the minus cs Laplace transform of f of t. Okay, so the variable of integration is u. So let me just say f of u. Okay. Now, if okay, how shall I put it? Okay, the u is the variable of the integration. So instead of u, it's just a name, all right? It's just the variable we use for the integration. So, okay. So instead of using u, I can also use t. There's nothing against it. So I'm changing my variable again. So I can think of this as just, this is just the Laplace transform of f of t. Okay, so I'm looking at the Laplace transform of uct times ht, and I get e to the minus cs times Laplace transform of f of t. And f of t is related to h of t, remember, like this. So if I substitute this for h, I have Laplace transform of unit step function times f of t minus c. It is e to the minus cs times Laplace transform of f. This is what I get. So you see, when you multiply with the unit step function, you make a shift. You shift everything. The Laplace transform starts from 0. The integral starts from 0. But the unit step function shifts everything to c. So in order to shift it back to 0, inside the Laplace transform, I have to take f of t minus c. Okay, and this Laplace transform works for all values of s for which Laplace transform of the function f exists. Okay, so in order to use the Laplace transform of f, on the other side, we need unit step function times f of t minus c. So for example, the Laplace transform of, let's say, u2 of t times cosine of t minus 2. You see, since I have u2 in front of it, I need cosine of t minus 2. All right, so this is going to be, c is 2, so e to the minus 2s times Laplace transform of cosine t now. Once you multiply with e to the minus 2s, then it is the Laplace transform of cosine t. And we know that Laplace transform of cosine t is s over s squared plus 1. Okay, so s e to the minus 2s divided by s squared plus 1. You might ask, what if I have, instead of cosine t minus 2, what if we have just cosine t? Now, in this case, we cannot use the above formula directly because we have cosine t. To use the above formula, we need t minus 2. So what we do in this case is, for t, we need t minus 2, so we subtract and add the 2. And then we use the summation formula for cosine. This is cosine t minus 2 times cosine 2 minus sine t minus 2 sine 2. So, okay. So we distribute. Cosine 2 is just a constant. u2t cosine t minus 2. Minus sine 2 is also a constant. Again, I have u2 sine t minus 2. Okay, so this is cosine 2 is constant. I can take it out. And now for this, I can use the above formula, e to the minus 2s times Laplace transform of cosine t. Minus, again, sine 2 is constant. For this, again, I can use the above formula, e to the minus 2s times Laplace transform of sine t. So I have cosine 2, e to the minus 2s, s over s squared plus 1, minus sine 2, e to the minus 2s, 1 over s squared plus 1. The coefficient of t is 1, so Laplace transform of sine t, the coefficient of t divided by s squared plus the coefficient squared. Coefficient is 1. Okay? I hope you see how to use this step function. As another example, I guess this is example 3. For example, if you have U4, I forgot. Okay. What is the Laplace transform of U4t times e to the power 3t minus 4? So I have U4 and t minus 4. So this is e to the minus 4s times Laplace transform of e to the 3t. So e to the minus 4s, Laplace transform of e to the 3t, 1 over s minus 3. Again, what if we have, instead of t minus 4, what if we have e to the power 3t? Again, as we did above, we need t minus 4 since we have the step function. So we subtract 4 and add 4. And then this is e to the 3t minus 4 times e to the power 12, right? 3 times 4 is 12. And e to the 12 is just constant. I can take it out. And for this part, e to the minus 4s, Laplace transform of e to the 3t, which is 1 over s minus 3. Now, if you remember in the previous video, we had some partial functions, and we wrote them using unit step functions. So we can now compute their Laplace transform. So this is example 1 from last video. Well, I don't know if it is the example 1, but example 1 at the end of last video, because in the beginning we did some other stuff, so maybe it's not at the end of last video. We had this function g, and we write it as t plus u1t times t squared minus t plus 1. Go back to the previous video. I'm sure you can find this example. So now the question is, what is the Laplace transform? Okay, t is easy. Laplace transform of t is what? 1 over s squared. Now for the rest, we have, okay, Laplace transform of t plus Laplace transform of u1t times t squared minus t plus 1. Now, since we have unit step function u1, inside we need t minus 1. Okay, so what is Laplace transform of t? 1 over s squared. So whenever I see t, I subtract 1 and add 1. And then I keep the t minus 1. So t minus 1 plus 1 squared. T minus 1 squared plus 2 times t minus 1 plus 1. And then again, separate minus t minus 1 minus 1, and then plus 1. So t minus 1 squared, 2t minus 1 minus t minus 1, so plus t minus 1, plus 1 minus 1 plus 1, so plus 1. Okay, so because of u1, we have e to the minus s, c is 1 here, times Laplace transform of t squared plus Laplace transform of t plus Laplace transform of 1. So let me go back here. Laplace transform of t squared, 2 over s cubed. Laplace transform of t, 1 over s squared. Laplace transform of 1, 1 over s. So 1 over s squared, e to the minus s. If we get the common denominator here, common denominator is s cubed. So 2 plus s squared divided by s cubed. But you don't really need to do that. Okay, so in the last video, we had another example. So example 2 from the end of last video. So our function was, or maybe I should go to the next page. And maybe I should check, just one moment. Let me check. Okay, yes, example 2, you see? Oops, I changed the file. Okay. And this was example 1. This is the one we did, we just did. And then the one I'm going to do now is example 2. Yes, so this is correct. Save now. Okay. So where am I? Yeah. So example 6. So this is example 2 at the end of last video. The function g we write as u2 times t minus 2 plus u3 times 6 minus 2t plus u4 times t minus 4. In this case, the Laplace transform. Okay, so it is this example easier, I guess, because for u2t, we already have t minus 2. For u3, we need t minus 3, but if we factor out minus 2, we have t minus 3. And then for u4, we have t minus 4. So this is e to the minus 2s Laplace transform of t plus, minus 2. I have the coefficient minus 2, e to the minus 3s Laplace transform of t plus e to the minus 4s, again, Laplace transform of t. So e to the minus 2s minus 2 e to the minus 3s plus e to the minus 4s divided by s squared, because Laplace transform of t, 1 over s squared. Maybe we can do just one more example. Example at the beginning of this video. We write, remember, square wave function. 1 minus u1 plus u2 minus u3. So if you take the Laplace transform, this is simple. Laplace transform of 1 is 1 over s. Laplace transform of u1, e to the minus s over s. Laplace transform of u2, e to the minus 2s over s, minus e to the minus 3s over s. So all the denominators are s. So we have 1 over s times the sum n from 0 to infinity minus e to the minus s to the power n, right? Because for n equals 0, it is 1. For n equals 1, minus e to the minus s. For n equals 2, plus e to the minus 2s, and so on. And remember, we take s positive because Laplace transform of 1 is 1 over s for s positive, minus e to the minus s in absolute value, it is less than 1. So this infinite sum using the geometric series, 1 over 1 minus e to the minus s. So 1 over 1 plus e to the minus s. So the Laplace transform, then we multiply it with 1 over s. So 1 over s times 1 plus e to the minus s. It's a cool example, huh? And this is for positive s. Okay, so these are just some examples on how to compute Laplace transform of partially defined functions. And now we can use this to solve differential equations, linear differential equations, when the function on the right side of the equality is piecewise continuous, or any partially defined function. We can now use the Laplace transform of unit step functions. We can write our function using unit step functions and then compute the Laplace transform and proceed as before. And this is what we are going to do in the next lecture. So that's all for lecture 22.